Hi there. I'm feeling like it's really important to talk about hybridization of atomic orbitals to create hybridized orbitals. I'm getting a lot of questions about them, and some people have seen my short videos about them and seem to want more. So I decided to make a longer video that goes through some of the fundamental principles of hybridizing atomic orbitals and drawing the orbitals, but also looking at the orbital energy diagrams. So hopefully all this is helpful for you. We will be talking about sp3, sp2, and sp. Okay. So let's start out with a black. I've got, at this point, 4 different colored inks for my fountain pens. And it has been so much fun using all of them. Okay. So first off, I wanted to start with talking about these fundamental principles of knowing when a hybrid orbital is even used or necessary. And so part of this is that can help you with it is thinking about what is the molecule. You need to know what the molecule is you're starting with in terms of its Lewis dot structure. So you first start out by looking at the Lewis dot. And you want to ask yourself some questions. And one is, how many sigma bonds are there? Okay, so I'm going to write out the word sigma, but of course, the Greek letter, sigma, that's what we usually use, right? Okay, so how many sigma bonds? And all this has to do with around the central atom, okay? You also want to ask how many lone pairs are there? Okay, and again, we are looking at the central atom. You can, of course, look at other atoms, but then you'd be looking at a different hybridization for those. We're just going to focus on central atom. Okay? And then, from knowing the answer to these two, this tells you how many hybrid orbitals you need. Okay? So, if you have 4 sigma bonds and no lone pairs, then you need 4 hybrid orbitals. If you have 3 sigma bonds and 1 lone pair, you need 4 hybrid orbitals. If you have 2 sigma bonds and 2 lone pairs, that adds up to 4. You need 4 hybrid orbitals. So if you can answer this question, you then know how many hybrid orbitals you need. Okay? And if you need 4 hybrid orbitals, if that is the answer to your question, that means that it is sp3 hybridized. Okay, if you add them up and it ends up you only need 3, then that means it's sp2. Or if if it's 2 hybrid orbitals, then it's sp. Okay, now notice how, use a different color here. An sp3 hybrid orbital comes from adding together an s plus a p plus another p plus a third p. There are 3 p orbitals, hence the superscript 3 there, plus the s. Okay. Hybrid orbitals follows linear combination of atomic orbitals, it's called, that method. Okay. And essentially that means if you have 4 atomic orbitals, you will get 4 hybrid orbitals. 4 hybrid orbitals. Okay. Meanwhile, sp2, s, and then there are 2 of these. sp comes from combining s orbitals with p orbitals. Okay, now you might be wondering, well, what about the other p orbitals? We know that there are 3 p orbitals that exist for atoms, px, py, pz. Okay, that means here there's a p orbital that is unhybridized, that is left over. Okay, I'm going to just abbreviate that. Here, there is a p and a p. There's 2 of them left that are unhybridized. Okay, these, in almost every case, these are used to create pi bonds. Okay. There is one case that I can think of where there's a leftover unhybridized p orbital not used for pi bonding, and that's for boron. So that's an exception. So we're going to put boron aside and just look at all the vast majority of cases where sp2 hybrid orbital has an unhybridized pure p orbital left behind that is then used for 1 pi bond. Okay. And just for completion of that thought, when it's sp hybridized, there are 2 p orbitals left over unhybridized. Those are to create 2 pi bonds. Okay. So this assessment of your starting Lewis dot structure works very well to figure out what kind of hybridization is happening. Okay, so let me set these pens aside and let's look at some examples, okay? I have so many things on my desk. I have molecular model kits and pens and papers and calendars, all sorts of things. Okay. So let's look at examples, okay? And we can see how this works when you're assessing the situation. So let's look at everyone's favorite starting point, methane, CH4. So if you do the Lewis dot of this, you see that around our central atom, there are 4 sigma bonds. That means we need 4 hybrid orbitals, and that means it must be sp3. Okay. If we look at NH3, we draw out the Lewis dot. There is a lone pair, we've got our hydrogens bonded to that nitrogen. And we see that there are 3 sigma bonds. I'm going to start right using this notation so we can be a little bit more efficient. And 1 lone pair. That means 4 hybrid orbitals. See how great this works? It must be sp3. Okay. And if we look at water, right, very similar, where we add everything up, we've got 2 sigma bonds, we've got 2 lone pairs, 4 hybrid orbitals, sp3. Okay. All 3 of these examples, when we look at the shapes of them, they're all starting out with this, in terms of the electronic structure, sometimes it's called, gives us a starting point in terms of saying this is tetrahedral and the bond angles are consistent with that. Here we have 109.5 degrees for methane. That's true for all of these bond angles, okay? And for something like NH3, ammonia, because of these lone pairs are strongly associated with this nitrogen atom. The pair is not stretched over the length of the bond being shared between the 2 atoms. So what it does is electron-electron repulsion causes these bonds to get squeezed together slightly. And so we've got a little bit less than 109.5. Okay? But the baseline is 109.5 because these orbitals, all 4 of them, are sp3 hybridized. And one of those hybrid orbitals right here is housing the lone pair. So hybrid orbitals are used for sigma bonds and lone pairs. All right, same thing happening with our water. We've got hybrid orbitals housing these lone pairs. 2 of them there, 2 of them there, and those are pushing down on these electrons in the bonds, pushing them away from each other, so they're even less than 109.5. All right, so in terms of shape names, we've got tetrahedral, we have trigonal pyramid, and we have bent. Okay. Now what about when we do our assessment? Let's go back up here where we were starting out. You look at the Lewis dot, and you look at how many sigma bonds there are and how many lone pairs. And let's say you determined there are 3 and you're getting sp2 hybrid orbitals. Okay, so what is possible there? Let's spin this around. Okay. All right. And let's look at a couple examples. So how about if we have formaldehyde, okay, CH2O. Okay, so the Lewis dot structure is double bond to the oxygen. There's the lone pairs. And sigma bonds to the hydrogens. Okay? So here, if you're assessing the situation, oh, pardon me, and looking at the number of sigma bonds, one of these is a sigma bond, but there is a double bond. So one of them is a pi bond. Okay. So that means that this molecule, the central atom on it, the carbon, needed 3 hybrid orbitals. That corresponds to sp2. Okay, so we have 3 sigma bonds, sp2, and we have 1 pi bond. Okay, now for the pi bond, we need 1 p orbital. Okay, 1 unhybridized p orbital. Well, thank goodness we didn't hybridize all of them. We only hybridized 2 of them because now there's 1 left over, and that can overlap with a pure p orbital from the oxygen. Okay, so let's look at this from a side angle. Okay, this is more of a bird's eye view looking down on the molecule. So if we just use this as a trigonal planar kind of structure, we're now going to turn this on its side and look at it from the side. All right, so I want to draw this. There's our carbon and our oxygen. And I'm going to draw these. Maybe I'll use red for this. I'm going to draw a sp2 hybrid orbital. Now, there is another smaller lobe on this side. I'm going to ignore that. Okay. This is our sp2 hybrid orbital. Okay. There are 3 of them, right? They're 120 degrees from each other. 120 degrees. Okay. So, we're looking at the side. So I'm going to have this kind of coming towards us. And then this one is going back behind. Okay, these are both also the hybrid orbitals, the sp2. So again, this is what I'm trying to do, is instead of drawing it flat like that, I'm turning it like this. So one's coming towards you, the other one's going back behind, and then this one is in the plane of the paper. This one. Okay. Now, I'll label this one for completion sp2. Okay. Now, let's put in our hydrogens, okay? Because our hydrogens, those just have the 1s orbitals. Those can overlap, and they are creating, I'll try that one a little bit bigger so it's closer to us, kind of a larger and closer perspective drawing. Okay, so here we have created a sigma bond. Here we have created a sigma bond with our hydrogens. Okay. Now with the oxygen, this will also be sp2 hybridized. It's got a sigma bond, so it needs a hybrid orbital for that. It's got 2 lone pairs. It needs 3 total hybrid orbitals, and it has a double bond, so it also needs a leftover p orbital. Okay, so in this drawing, let's also draw the sp2 hybrid orbitals for the oxygen. Okay, so there's one of them, sp2 from the oxygen, and then we have one coming out towards us and another one going back behind. Okay, these two house the lone pairs. Okay, but what's missing, but we're about to draw it in, is the unhybridized p orbitals. Okay, put this pen back for a second. All right, the unhybridized p orbitals, these are perpendicular to this plane, above and below. Okay, here is the 2p orbital for the carbon. So again, here's the plane of the hybridized orbitals. Here's the pure p orbital above and below the plane. And same with the oxygen, above and below the plane. This then allows electron density between these two to connect, overlap, above and below the plane. Okay, this is creating our pi bond, both above and below the plane. So electrons can be found, essentially probability is equal above and below the plane for this pi bond. Okay. All right. Now, what if you have a situation where it's sp2 hybridized, but instead of there being 3 sigma bonds, there could be 2 sigma bonds and a lone pair? Okay, so an example of this is SO2. Now, this does end up having resonance structures. I am just going to draw one of the resonance structures, okay? And I'll put that here. One resonance structure. Okay. Would look like this. For sulfur, it's got a lone pair. And we have double bond to one of the oxygens. Again, this is a Lewis dot. Okay, so we've got, holding 3 pens all at once, we have a sigma bond there, sigma bond there. We have a lone pair, and we have a pi bond. Okay, so from the central atom, the sulfur, its point of view, it's got a sigma bond. It's got 2 sigma bonds, one on each side, and one lone pair. Okay, so it needs 3 hybrid orbitals, because remember, hybrid orbitals are what what are used for sigma bonding, and they're used for housing lone pairs. Okay, these hybrid orbitals, they are reaching directly out from the central atom, so that's why they're used for sigma bonding, as opposed to the leftover unhybridized p orbitals. Those are perpendicular to the other atoms. Okay, so this needs to be sp2 hybridized. All right, so if we were to draw, once again, our S atom, central atom, okay, and this is going to be tricky because that lone pair is going to be kind of back behind, but if we draw this is kind of cool because you get to see how the electrons are delocalized. We've got a sigma bond. So let's draw sp2 hybrid orbital from that, sp2 hybrid orbital, and then our sp2 kind of going back behind off to a side. I guess I'll do it that way. Okay, there's our lone pair. Okay, now meanwhile, the oxygen atoms, they will also be sp2 hybridized. And now I'm going to show you why I'm having both of these oxygens be sp2 hybridized. Because when you have resonant structures, what is actually going on is an average between the two. So you essentially have 1.5 bonds. Okay, the strength of these bonds is stronger than a single bond, but not as strong as a double bond. Okay, that's what we're looking at here. And the way that happens is with the resonance, it's actually because this electron pair is delocalized. It is shared on both sides. And so let's finish up with the lone pairs on the oxygens. These are sp2, sp2. All of these are sp2. And these are lone pairs. Okay, these are all sp2, sp2. Oh, and then here's the other sp2 on oxygen. Okay, so these are all overlapping here to create sigma bonds. And then we've got all these other hybrid orbitals that are housing lone pairs. All right. And then we have the unhybridized p orbitals. Okay, so this sulfur has this unhybridized p orbital, right? So it had sp2 and then one p orbital. This oxygen did the same. Okay, but you know what? This oxygen did the same as well. Okay, these are identical, these two oxygens on both sides, and they each, I guess I'll just put that in there, end up overlapping with the p orbital with the sulfur. So we've got this pair of electrons that is being shared amongst all three atoms. Okay, so what we have in here are delocalized, we call them, pi electrons. All right, this is something that we observe in resonance structures. Okay, it's kind of nice drawing this out like this because it explains a lot more accurately what's going on rather than resonant structures where here I just drew one of them, but let's just go ahead and let's say, let's show both of them. The Lewis dot representation of, let's see, I'll put that there, of resonance structures is just very misleading. you know, because it's saying we have an oxygen here with 3 lone pairs, and that's simply not true. We show an oxygen with just a single bond on one side, not true. We show a sulfur-oxygen double bond. That's not true, all right? It's actually 1.5 bond strength. So Lewis dot resonance structures are a little disingenuous, and I feel like it just makes things more confusing because you imagine it's flip-flopping between the two or something like that, but actually it's an average between the two. And this model of hybridization helps see how that can happen. All right. If you move forward out of hybridization, which is called valence bond theory, if you move towards molecular orbital theory to look at delocalized electrons, the model is a bit more sophisticated. It's a bit more accurate, and but I feel like once you've learned about hybridization, this is a really nice model to see how those electrons can be shared amongst, like we have one pair that's shared amongst 3 atoms, okay? And it helps you see how it could be 1.5 of a bond, 1.5 bond strength, because you have this essentially this big pi orbital above and below the plane, and you have 1 electron pair that is spending time within that space. So, I like it. Okay. So, wow, that was a little bonus sidetrack slightly, talking about delocalized electrons and resonance structures, but resonance structures are so common that I think it's very helpful. Okay. All right. One last comment. In terms of shapes, we saw with sulfur dioxide, it's bent, and we have trigonal planar for our formaldehyde there. All right, one more example, and we are going to do carbon dioxide, okay? So with carbon dioxide, we are going to look at carbon as our central atom. So we've got carbon flanked on either side by oxygens. Each of those has 2 lone pairs. So if we look at this carbon, which has its octet, no problem, okay, but it's got sigma bond, and pi bond, okay? So, looks like this carbon needs to be sp hybridized, okay? It's got 2 sigma bonds. It doesn't have any lone pairs, okay? So, it's got to be sp hybridized. Also, it has 2 pi bonds around it. Okay, so that tells us, all right, good thing that we hybridized it to be sp, because we need 2 p orbitals to create those pi bonds around the central carbon. Alrighty, so let's look at what this looks like. We have carbon, oxygen. All right, we've got sp hybrid orbital on one side. There's a small lobe over here that goes with that, but it's tiny, so I'll just leave it out. And we have another sp orbital that is there. Okay, so this is sp on the carbon, either side. The oxygens here, meanwhile, these are sp2. Oxygen needs sp2. Okay, it's hard to draw on there. Just put it in there. Okay, sp2. oxygen needs sp2 because it's got these lone pairs, right? So lone pair there, 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 there. Okay, let's start over here. Let's draw these p orbitals. Actually, we can draw them in. Let's see. I want to start. Actually, I'm going to do it here to start. On the carbon, there is one of the unhybridized orbitals, p orbitals, and it needs to be perpendicular, it needs to be parallel in the same plane as the p orbital with which it is forming a pi bond. Okay? So with this oxygen, the way I've drawn this here, these two p orbitals can overlap because they are in the same plane. All right? So what that means about this oxygen and its sp2 hybrid orbitals is that they are perpendicular to this p orbital. So one's coming out towards us with its lone pair, and then this other one's going back behind it over there. Okay, so this is the plane of the sp2 hybrid orbitals. Here is the perpendicular p orbital that's overlapping with the carbon and creating a pi bond. Okay, so there's a pi bond there. But we have now used this p orbital on carbon in this plane to create a pi bond with this oxygen. That means for this carbon to also create a pi bond with this oxygen, it can't use this p orbital anymore. It's done. It's not like over here where there was resonance with SO2. We have to create localized bonds here where that electron pair can stay between the carbon and the oxygen in this pi arena. And then this carbon and this oxygen need to use a different set of p orbitals to overlap. So this p orbital is now going to be perpendicular. Oh my gosh, how am I going to do this? I don't know. It's coming out at us. It's the problem. That's the challenge with drawing. It's coming out towards us. I wish I could have it come out right at us, coming sticking straight out. So I'm going to try to draw at an angle. This is using my purple pen. Trying to distinguish it. Okay. And then that one is going back behind. Okay. And then the oxygen p orbital has to be perpendicular to this, so this is coming out also towards us. Okay, I'll try to draw it. I'm making it thicker, so maybe you can see the purple better, but I'm just not seeing it, so I don't know if that's helpful or not. And that goes back behind. It's kind of behind this. I wish I'd waited to draw that sp orbital. Okay, I'm just going to put it kind of behind it, maybe. Ugh. I don't know. It's back there. Okay. So now these two are going to overlap. So electrons can be shared in this plane, and then these back here are going to be overlapped. They're back behind the paper. I'll draw like that. Oh my gosh. This is really challenging. Okay. So this is now, these p orbitals are coming up towards us, going back behind the paper. All right. And so that means that these sp2 hybrid orbitals with the lone pairs, those are actually in the plane of the paper. So they're still there. So, oh my gosh, there's a lot going on around this carbon atom. We've got electron density forming a pi bond that is in the plane of the paper, and then we have another that is perpendicular to the paper where there's electrons being shared in those pi bonds. So here's one pi bond, I'll put this here, this one, and then we have a pi bond here, this one. Okay, so we just took into account this pi bond and this pi bond, but really looking more spatially how they are different, that these are in two different planes. All right, so pretty cool. And we also saw how we got sp hybridization, how we needed that to not only create the sigma bonds between the carbons and oxygens, but also to leave behind the p orbitals and have enough p orbitals on that central carbon so that it could overlap with a p orbital on one oxygen on one side, and then in a different plane interact with p orbital from the other oxygen on the other side. All right. One last thing. This is linear in terms of the shape, and it is 180-degree bond angle from oxygen, carbon, oxygen. All right. That is a wrap. I hope that was helpful. Oh my gosh, I feel like I used more different pens on this video than ever before, like mixing them up and actually kind of needing them. So, all right, thank you for being here. I really hope this hybridization lesson helps you understand hybridization a little bit better, and when you need each kind of hybridization, and just having a little bit more depth of knowledge on this theory, valence bond theory, that shows hybrid orbitals. Okay, so continue with your requests for videos. I'm very happy to make these for you. I really appreciate all of you for being here with me, for listening, for watching, and so happy that you are learning some chemistry with me. I love teaching, if you can't tell, and I also love drawing, doodling, all this. It's just such a joy for me, so I am happy to be here, and keep on those requests, and please do like and subscribe to my channel. It really helps me a lot, and there's several aspects to that. One is it just it's warm fuzzies for me, honestly. It feels really good to know that I'm appreciated, that these things I share with you are appreciated. So it helps with that. But it also, if this channel continues to grow, it will allow me to create more and more videos that will help more and more people learn chemistry in this way. I really like teaching slowly, clearly as I can, calmly, so that you can learn in a very low stress environment. I think that's very important. And maybe even if you're not interested in learning this, I hope it is calming and it's just something you can listen to that you enjoy. So, all right, that's it for now. Thank you again, and I will see you in the next video.